This afternoon we are going to discuss about link loss calculator. So we are going to discuss in two aspects. One is in the data center, another in the enterprise building. Also on this session we will discuss why the power budget is important, what are the components are involved while working with the link loss calculator. So let's get started. This is the agenda for today. Like we are going to talk about that fiber loss calculations, and we are going to talk about some power. What is the difference between power budget and loss budget? Then we will be discussing about ComScope link loss calculator and few examples which we are going to discuss during this session. Okay, actually this is the questions. Like, do you know your power budget for your applications? Okay, this is very interesting and important questions. Like nowadays, we are asking a lot of end users, a lot of consultants, why it's important to ask, or why should we know before designing any data center or any building backbone. Recently, we have involved two major projects in this region. One is in the data center, other one is the enterprise building. I will tell you our conversation with the client, with the consultant, how we started, then how they felt the importance, knowing that losses or link loss calculation, why it's so important for them. So here in the data center, actually like a customer started, like we asked customer like what kind of topology you want to deploy in the data center. Customers said like, Moti, we are going to do two-tier topology where we are going to put spine and leaf switches, which means all the racks will have a top of rack switches or leaf switches, and where MDA they are going to host the spine switches. So how many racks in the data centers? It's roughly 450 racks in the data centers. The customer said like, Murthy, if you are putting YM4 or YM5, it will be sufficient because it can support up to 550 meter. In ComScope by standard, it's around 450 meters. So we said, okay, customer, you want to put a YM4 or YM5, it's a good, but I'll be very cautious before going with YM4 or YM5 in the data center. The reason behind, like whatever we standard we know today, okay, it's not applicable anymore inside the data centers because the data center is demanding more bandwidth, more applications. Okay, so in this slide, what you are looking at here, if you go with the 40 gig based ESR4 transceiver, the maximum length you can run YM4 or YM5 cable in the data center. It's 490 meters. If you look into that similar BiDi, which we use very frequently in the data centers, the BiDi transceivers for the 40 gig, by standard, it's around 130, 140 meter, but with ComScope ultra low loss solutions, you can run up to 190 meter. So you can see here, there is a different approach when you go to the data center because you should know your application, what kind of application the customer is going to run inside the data center. Based on that application, defining your cable length. So it took some time for a customer to understand, okay, so I cannot follow the traditional way of how I calculate length. So I should know what kind of application I'm going to run on this data center. Based on that, I have to choose the cable. I have to design the cabling design in line with fitting to the applications. If the customer put the cables first without knowing the application, then probably in a period of year two, he need to redo his cabling because that everyone agrees in this call that application is getting faster development compared to the cabling changes, whatever we are going to do inside the cabling. So this is happening inside the data center. So you should know what is the application you are going to run. Then based on that, you should design your cabling network. When it comes to the building, why it's important? We are talking about always 10 gig. 10 gig is maximum sufficient for any backbone. So I'm moving to the next slide. Actually, this is the link loss calculation, which we are going to be the topic of today. We need to know accurate measurement and testing in fiber cable insulation are critical to ensure overall network integrity and performance. A significant signal loss in the optical fiber can cause unreliable transmission. So what is the optical fiber loss budget? The fiber loss can be also called fiber optic attenuation or attenuation losses, which measure that amount of light lost between input and output. Fiber loss budget is affected by many factors such as connector loss, splicing loss, and bending loss, etc. So how can we know the value of losses on the fiber link? This is where the fiber performance calculator from CommScope comes in. Care needs to be taken if comparing to application optical power budget, as these are now complex mix of bandwidth and attenuation. The terms power budget and loss budget are often confused for many of us. The power budget refers to the amount of fiber optic loss that link can handle in order to operate properly. Sometimes the power budget has both a minimum and maximum value, which means it needs at least a minimum value of loss so that it does not overload the receiver, and the maximum value of the loss to ensure the receiver has a significant signal loss to operate properly. The loss budget is the amount of loss that fiber link should have if it is installed properly. It's calculated by adding the estimated average losses for all the components used in the fiber link to get estimated total end-to-end loss. The loss budget has two uses. I want to insist when you are planning for the loss budget, we can have two uses. One is during the design stage. It's used to ensure the cabling being designed will work with the links intended to be used over it. And after installation, the loss budget for the cabling is compared to the actual test result to ensure the cable plant installed properly. Obviously, the power budget and loss budget are related. Fiber link will only operate if the loss is within the power budget. This I want to reiterate. The fiber link will work only if the loss operate is within the power budget. Always remember, the calculated loss budget is an estimate that assumes the value of component loss and does not take in account of uncertainty of the measurement. So we are going to talk about here some of the component performance which will impact your link loss calculator. One of the important parameter which we talk in CommScope, the multimode fiber. Multimode fiber, CommScope always talks about DMD, which means the differential mode delay measurement is the only recognized test method for laser bandwidth in the fiber standard. What is DMD? Basically, it's measure of time delay for the slowest and the fastest path through the fiber. Note that our criteria exceed the standard in many areas. Tighter criteria lead to more information. It was development tool first, then the test method. The red window is really just time difference. It could have been just the vertical in bars. So in the slide, you can see here, like we are using a single mode laser, which is a 850 nanometer to test the multimode fiber. Okay, typically the differential mode delay, they talk about the quadrant. Okay, so what we have normally do in our laboratory, we use a 300 meter length of sample fiber. When you look at the TE standard, we refer, okay, you have to fire 100 picosecond pulses per 2 micrometer interval in one quadrant. You can see here there are 4 quadrants. Okay, center of the core was not tested for the majority fibers supplied today, which is needed for about 10 gig. Because differential mode delay is one of the key parameters if you want to run a high bandwidth requirement like a 40, 100 and 200 gig. CommScope, we do test in the central core of the fiber, which is the first quadrant, and we do all the 4 quadrant tests to ensure that the fiber is highly capable to handle the current and future bandwidth requirement. So that's what we insist all the designs. So you need to follow that differential mode delay measurement is a critical. It's very important to test all the 4 parameters. When it comes to the single mode, okay, there is always the discussion, what is OS1, what is OS2? You can see the table over here. This table is extracted from this IEEE standard. Okay, here you can see YM3, YM4 multimode as well as YM5 multimode losses. It's almost around 3.5 to 1.5 for YM3 and YM4. And YM5, it's around 3 dB and 1.5 dB. Where OS1, which is the tight buffered cable, it's around 1 dB at 1310 and 1383, it's a 1. And 1550, it's a 1.0. Actually here, normally whenever we go and refer the standard, it says either 1310 or 1550. Now standard also makes sure that at 1383, which is widely used for the 0 water peak fibers, should be at 1 dB at 1383 also. So here, just I want to give one important point everybody need to remember. Sorry, when we are talking about loss for the fiber, we are not talking about the loss for the fiber glass. We are talking about as a complete cable. So how we are jacketing, whether the cable is going to be a tight buffered or loose tube, this is the one going to give you your total losses, not glass only. So whenever we talk about this losses, we are talking about when tight buffered cabled losses, not the glass losses. In CommScope, the tight buffered cable, we are talking about less than 0.5 dB for the tight buffered. In loose tube, we will talk about that less than 0.34 dB at 1310. This is about the cable. There are some more parameters associated when we are going to make a link. One is the cable, other one is the connector. So here you can see in this slide, this is standard-based attenuation for multimode connectors. It's caused by the standard. In the below, you can see the 7 different images. Okay, one is the core diameter, the first image. Then other one is the core clad image. Another one is the core non-circular image. Another one is a numerical aperture where we are launching the fiber power into the fiber. Then there is other type of parameter, which is the extrinsic parameter. One is the angular error, another one is the lateral error, and the physical contact of fiber cores. Okay, here you can see all these values. There are some tolerance they are giving. Example, the core diameter in the 50 micron, which is the multimode, is a less than 0.2 should be there, and 6% tolerance. When we go for the core and clad, we will get less 0.01 dB. Okay, comparing with this, the maximum attenuation due to the fiber match is allowed 1 dB in the factory. Okay, this values, whatever you are seeing in the red color, it's in the factory values. Then attenuation influenced by the quality of ferrule. Actually, the connector will come with the ferrule, right? That ferrule also have a certain attenuation that is also should be within 0.5 dB. Then attenuation influenced by the end phase geometry, which we normally talk about angled polish or physically polished contact, which is 0.7 dB. So these are the values defined by the standard. But when you see for connector loss, the mated connector, we should have a 0.75 dB. So every manufacturer who manufactured the connector, we have to put a lot of effort to bring these values less as possible during the manufacturing process. This is what we are seeing here. This is for the multi-mode connectors. When you move to the single mode, it's more difficult because the mode field diameter for the single mode, it's 8 to 10 micron. So here attenuation mismatch due to the fiber parameter, it should be within the 0.4 dB, and attenuation influenced by the ferrule, quality of the ferrule, it's 1.9 dB, and attenuation influenced by the end-phase geometry, whether it is angle or a physical contact, it's a 0.7 dB. So this is the image you can see downside of the slide, there is a more field diameter mismatch, core clad, and angular error, and lateral offset, and axial separation of cores. Okay, combining all these losses should be less than 0.75 dB during our manufacturing process. Almost all the vendors who manufacture this kind of connector, they are extremely careful, and they are working very hard to bring these values low as possible. So now talking about the link loss budget, calculating a loss budget for an optical fiber cable simply involves estimating all the common losses, fibers, splices, and connectors, and adding them all together. The cabling standards identify the maximum allowed loss for each component. As you can see, the connector loss is identified to maximum value of 0.5 dB, 0.75 dB, and the splice losses are around 0.3 dB. And also different values for the fiber attenuation of multi-mode and single-mode fibers at different wavelength. So for example, if you have a link with the 2 connectors and 3 splices, then we multiply 2 into 0.75 dB and 3 into 0.3 dB, and adding them up, the cable attenuation to get the link loss budget. It's due here to mention that the CommScope fiber component not just meet the standard, but also provided better performance through the better losses. Okay, this is the important slide. Just I will probably ask all the audience where to start. Where should be our starting point during the fiber cleaning process? We should first clean, or whether we need to start first inspecting the connector. So what CommScope by the standard is recommend. Okay, when we are taking the connector from the packet or removed from the patch panel, first we need to inspect the connector. If it is clean, then you have to connect, and then you can proceed. If it is not clean, then you have to clean again, then inspect. So I want everyone to remember the starting point for us. First, we need to inspect the connector before cleaning. This is also adding some losses to our link, so we need to be extremely careful before cleaning. First, we should inspect the connectors. I have certain examples over here. You can see here, CommScope. You can see in the picture, there is a 4 component. One is the patch card, another 2 modules. Third one is the trunk cable. I'm giving the example for your data center. The standard connection can have up to 0.75 dB attenuation. So if you compare, there is a 2 LC modules over here, which is 1.5 dB. Then 2 module losses around 3 dB. Then we assume that cable losses around 100 meter, which is a 0.35 dB. So we have total losses 3.35 dB. When we will get this value? Using a component claiming to meet the standard. And I want to insist here, the mixing component from the different vendor, even if they claim better performance, these values, we have to follow the standard values, which will be 3.35 dB. You can see one small graphical representation in the right side. Okay, here you can see when I'm saying 0.75 dB, the good connector should fall between the middle of the line, which is around 0.375 dB. When people say typical and average, it's always should be around 0.375 dB when I have a pair of connectors. So this is the typical example what we do in the data centers. When I move to the next slide, okay, this is just, I want to give us some clarity on what is some people say it's average or typical numbers, or some people say it's a maximum value. So which one we need to trust, or how we need to look into these values. So what does mean that average or typical mean? This module insertion losses 0.18 dB is average. You can see here when I say that typical value here, the average value or a typical value for the MTP Elite connectors, they are saying it's a 0.10 dB. And the IL maximum, they are claiming it's a 0.35 dB. If you say the premium connectors, they are claiming at 0.08 dB. and the maximum they are saying 0.15 dB. But technically, okay, it means nothing. Some links will be better, some links will be worse. You cannot take two modules and expect it will give you 0.036 dB. Okay, this typical always is a critical. If you see in the right side, the best connector always should be 0.1 dB, which means it's exceeding that IL maximum value, which is a 0.35 they defined, but they are getting at 0.36. If you are taking the exact same batch of modules, same connectors, but typical average value, it's always no need to be the same value. When you say average, means the patch card can have a 2 or 3 different values during the manufacturing process. So we care about the worst channel, not the best or average. The model will promise 0.5 dB max. If you mix two combination connector, will give you the maximum attenuation of 0.75 dB. If you come to the ComScope, like you're saying, okay, this average and the typical, it's very, very critical numbers, because we cannot work based on this critical and typical value, because it can be worst or it can be best for all the batches of the product they are manufacturing. What is the ComScope approach? ComScope approach, the optical specifications in the multimode. We say always the insertion loss is 0.35 dB. I want to reiterate here, we say 0.35 dB maximum. It's not the factory performance, we say it's in the field performance. So we are defining the maximum value of the 0.35 dB. We can get a link loss 0.7 dB plus cable loss. Average or typical will be lower. If you mix our model again with any other vendor, it's around 1.5 dB per module. The loss will go here. So what is the message I want to give here? If you use ComScope, connector, patch card, and pigtail, the loss what we are publishing, it will be inline. If you are mixing with, example, the link and the module from ComScope, but the patch card from some other vendor, there are possibility it will go back to the standard value, where we will have a 0.75 dB per connector. Then you can see in this table, this is the power budget is typically mentioned in the IEEE Ethernet standard for application on both multimode and single mode. The slide here shows some of the power budget values that are mentioned in the IEEE. You can see number of fiber, example 10G base, SR, the two connectors, the loss is 3.1 dB, and 25 gig base SR, the loss is 1.9 dB, and 40 gig, the loss is 1.9 dB. So if you look at this power budget, actually I want you to remember this power budget value. If you remember 4 slides behind, we did small calculation on the link loss budget, which is the 3.35 dB. If you go with that loss, none of application will work here, because each application required different type of power budget required to work. So people ask many times, which standard I need to follow? I need to follow cabling standard, or do I need to follow the IEEE standard, or do I need to follow the vendor specific standard? We always recommend to go follow the IEEE, because IEEE is different the application requirement. That application will work better if you follow that application based power budget defined in the IEEE standards. Okay, sorry, this slide, what we are seeing here, this is the power budget for the single mode. Single mode is a 2 fibers. The power budget is 1.9, which is LC connectors. If you go to MPO, which is ASM4, that 8 fibers, where the power budget is limited to 3.2. This is the straightforward approach to calculate the link loss budget, just adding the component loss. Other hand, ComScope link loss calculator is a different approach. It's as it understands that every signal will be altered or conditioned after passing through a connector or a splice. Therefore, the loss in the next connector or splice will be different than the previous one. Now we are going to look into this, like what is the ComScope system approach, how the link loss calculator look like, how it can be helpful for during the design and implementation stage. Okay, this is a System Max link loss calculator. How do I get it? You can visit ComScope .com. You can go to the resource tab. You can choose the calculator. You can download the tool and start. When you're starting this, it's kind of Excel file. It's embedded with macro. It will ask you to enable editing. Then it's allow active content. So you can see in this window on the right side of bottom, the calculator looks like this. Okay, what about calculator? Is it available in either form, like app where we can have it in mobile? So if you want to use it as a handy, okay, there is an application available in the iPhone as well as the Android platform. So you can download our Linglas calculator by ComScope. You can keep it with you if you want to calculate something on the field or during your meeting hours. You want to see some Linglas calculator. Linglas calculator. If they want to use it, it will be very handy tool. You can have it in your phone. You can use it whenever you need it. So the Linglas calculator looks like the Excel form. Okay, where you can, if you need to calculate the several links, it's a good idea to name the links and both the ends. Then you can go to this next step, select the fiber type you need. Then you can input your total length of the link, what you needed. Then select the product combination that you need for the project. Confirm the configuration. If you want to delete the last item, clicking the item, you can delete it using that bottom right, there is option. So here you can see in the bottom, this is the guaranteed maximum loss of the link and the possible improvement by using a ultra low loss product. So here, this is the straightforward example how the Linglas calculator will look like, how you can populate those information based on your real-time or design experience. If you are looking for some calculator, this is the best tool for you. So end of this exercise, you will see in the right side. Right side is the one which is going to give the application assurance results according to the calculation what you have done. So it will show you in the right side this list of applications supported, okay, based on your configuration. So it will be very easy for you to identify, okay, at what length my application will run. If you are using a transceiver 10 gig based, yes, it can support up to 400 meter. Okay. If you use like a fiber channel FC, maximum you can put 95 meter. Here in this example, you can see that we have used 4 connectors, which means we are using 8 duplex connectors. So I will move to the next slide. I can show you some examples how it looks like. Before moving to the examples, just we have additional features like our Linglas calculator. It's a pre-built with the Fluke machines, the version of the Fluke machines. So which means is like if you have a Fluke machine, you can update to the latest version of the firmware. Systemax Linglas calculator comes with the version from 9.9, and during the setup of Systemax, actually it will ask you a couple of options. Like it will look like this. It will ask you input number of connectors, number of splices involved, what type of connector you can choose directly in the Systemax configuration in the Fluke machine. Once you have set all this configuration, then you can proceed for the directly testing. It can compare the actual measurement against the Linglas inputted during the design or installation. It can validate, then directly you can submit these files for the ComScope warranty purpose. Okay, this is the Linglas integration. Actually, most of the projects, actually now we are pushing our partners and the end user and consultant to follow this, and it will be very handy tool for us to issue the warranty, and even for the end user and consultant to ensure that the design everything is going to work for them. Okay. When it comes to the data center, probably in this slide you can see 2 different approaches currently followed. One is the 3-tier architecture, another one is the 2-tier architecture. The 3-tier architecture, like we have a core and edge and access switches, then the server network. When it comes to the two-tier, this is traditionally leaf and spine, where leaf switches are connected directly to the spine switches. Actually, this is the direct connections people who want to make in the data center from leaf to spine. But in real situation, we are not going to connect leaf to spine. It will go through always patch panel. So how we are going to do the cable? We are going to replace everything with some kind of MDA cabinet or ODF. Then we are going to do the cabling across through the MDA cross cabinet to connect spine and leaf switches through the cross connection cabinet. When it comes to the example for the data center, you can see here we have a leaf switch and a spine switch. In our previous example, it goes through the cross connection cabinet. Then this is the one patch panel. In the leaf switch also will have one patch panel. So you can see how many modules involved here. 1, 2, 3, 4 modules are involved. When you go for a standard based calculations, you will get a loss of 6.2 dB because it have a 8 number of connectors into 0.75 dB, then cable for a kilometer, then it's total 6.24 dB losses. If some vendor claims loss at 0.5 dB, if you multiply that, then you will be getting 4.2 dB losses. Where support application is required, the value should be less than 1.9 dB, then only the application work. If it comes to the ComScope System Max low loss solutions, it gives around at 850 nanometer 1.49 dB and 1310 nanometer is 1.39 dB. When it goes to the System Max ultra low loss, even the values are better. So System Max low loss and the ultra low loss, this connection configuration it will work. What we are doing here, 4 connector model, because we have a 4 modules between spine and leaf switches. I have another one example where we have a 6 modules between leaf and spine because we are extending the connectivity to the next port or next cage available connections. So which means you can see in the below picture, there is a cross connection cabinet, which is a ODF or MDA cabinet. This is the spine, but the leaf will be sitting another 2 cabinets, which is like we have one more cross connection in the leaf cabinet as well. So you can see there, switch, MBO cable, MBO patch cord, then MBO module, then trunk cable, again MBO, then we do have one type of cross connection. Then we are extending to another one cross connection where we have 6 connectors, 6 modules are involved. Total we have here 12 connectors. When you go standard based value, the total value is 9.3. If we are going with the vendor claimed values, which we are going to get 6.28. If we go with the System X low solutions, we are getting 2.06. If you compare that 2.06 against the application requirement, it's a 1.9 dB, where even System X low loss, it's a doubt whether it will work or not. But here, System X ultra low loss, definitely it will work because it's below that what the application needing value here. In summary, when you're designing the infrastructure for fiber network or even the data center, we need assurance that the infrastructure will support the intent application as well as the future application to ensure the smooth migration to the process speeds. The process starts at the design stage, for example, by identifying the data center layout, including the location of compute and storage equipment, spine and leaf switches, channel architecture, rack layouts, component and cabling distance. Ideally, the next step include the manufacturing modeling tool that can predict end-to-end channel loss budget based on the channel length and the component selected, which is the fiber performance calculator. Finally, the result from the calculation can be used to validate the application supported or to iterate the process and change the architecture and component selected if it is required. When the installation is completed, the links and channels can be tested with an approved tester. This also allows your fiber link to the eligible for the ComScope 25 years application assurance warranty. In other words, using the fiber performance calculator is mandatory for acquiring this warranty from ComScope. with that, I will conclude my presentations. Thank you very much for attending the sessions. And we are looking forward to our next webinar, which is going to happen in the month of April.